Welcome to Aerospace Structures 1. Today we'll be covering failure investigations. And the book for this course is the one here at the bottom. Ignacio Dapic, who is here pictured on the left, he's our invited guest lecturer. And we'll then continue the coverage of the understanding of failure modes in aerospace applications. And today the special focus is failure investigations. We can be covering analysis all day long and testing all day long, but really gaining an understanding of why analysis, testing, and all these things are important plays a key role in this course. But furthermore, when you work in aerospace applications, anomalies are very common. You're gonna get anomalies. You're gonna have failures that will occur that could cause a significant setback in the life of the program. As a consequence, I have decided to really cover what failure investigations are about. But failure investigations go beyond failure investigations. They go into even the design. For example, even before a failure occurs, we can predict when we won't know what's going to happen in the life of the program, but we can predict it by making sure that we covered all the failure modes and all the possible issues that could occur in the life of the program. And so that's why I think it's so important to discuss failure modes in the context of failure investigations, because it pushes your mind a little bit further in the design process, in the design mentality, especially when aerospace structures, launch vehicles, airplanes, and spacecraft have hundreds of parts that have to work really well together in a very unified way: proportion, structures, electronics, thermal, fluid mechanics, guidance and control, systems engineering. All that has to work well together for us to be successful. So today I want to invite Ignacio Dapic. He's a very close friend of mine and supports me through my hard times and through the good times. And Ignacio Dapic is an effective and creative passion leader with 17 years of experience on new product development. And he is now the offer management director of home and distribution. And he has significant experience, as you can see here, going all the way from structural simulations all the way up to where he's now. He has an education, an MBA at UCLA, and also he has a master's at Aerospace Engineering, Virginia Polytechnic Institute at State University, and we came from the same school, and a bachelor's degree in aerospace engineering as well. And as you can see here, a lot of people ask, what my career look like in the future. For example, I was a mechanical engineer as a bachelor's degree, and now I'm working on rockets. I had no idea I'll be working on rockets. And so this is a perfect example of having a career that can take you to different places and can make you very successful. And so that's why I think Ignacio it will be perfect for these conversations on failure analysis, coming from a different industry altogether. But I want to show you how similar we approach the problems. So Ignacio, over to you.
Thank you, Professor Goyal. How's everyone doing? It's a pleasure for me to join this class. Very excited. Greetings from Nashville, Tennessee. As Professor Goyal was saying, I have about 17 years of experience on product development. I've been in engineering. I've been in offer management. I've had the opportunity to touch a product at different stages of the design life cycle. I've been products become a reality ever since they were presented or discussed in a napkin, all the way to launching them into the market at a massive scale. As Professor Goyal was saying, I'm an aerospace engineer. I love aircraft. That was one of my big passions when I was younger. It's still a big passion of mine. The life took me through a different path, And again, I'm not in the aerospace industry. I'm in the energy management industry. But it's very similar in many senses how the aerospace and the energy management industries behave. There are a lot of implications. There are a lot of things at stake, and therefore the importance to really understand the effects that our actions have when developing a new product, a solution, a transportation vehicle, anything like that has very, very strong implications.
How failure investigations are conducted, and why testing is so important early in the design phase. And is it important to test the product as in service? Why is that important? Is it not? Maybe it's not important in your area. What is the role of analysis in your area, and why it can be beneficial during development cycle of the program and during failure investigations? I also am very interested in the top lessons learned from working challenging from you working challenging engineering problems in your area of expertise. And also I want to know more about what makes an engineer successful in a company. But as we go through this discussion, what I want to do is contrast your area with the aerospace arena. And so maybe sometimes I'll chime in and have that discussion with you, and then others in the class can chime in. What do you guys
Yep.
think? But before we do that, I want to bring back, everybody to a baseline, and remind everybody, what are we trying to accomplish? And in this course, what we're trying to accomplish is to gain an understanding of the design process and what we need to do to ensure that we can avoid expensive failures, that we can avoid people dying from airplanes crashing, that we're not losing space assets that are quite expensive. Um, we're trying to learn those fundamental building blocks that will take us there. And so that is the goal of this course. I want to teach you, and we want to bring this to you. We want you to keep in mind that when you go to engineering, it's not all about numbers. It's not about sitting down at a computer and just running a computer code. Engineering requires a system level view from testing, analysis, inspections, product quality assurance, and ensuring that we're doing everything we can to prevent catastrophes. And we want to also avoid expensive failures during test programs. Like the 777 is an example of that, where it set back the program because of these failures and that were discussed. So, we have failure modes. Here's the Haviland the Haviland Comet with a square window that experienced 13 fatal crashes and 426 fatalities. The issue here is were fatigue cracks initiating from stress concentrations located at square-shaped windows. And the point of this picture, which is very famous, is that after every failure, you learn something new and you can improve the design moving forward. And so just want to keep that in mind, because it's okay sometimes to have those failures, because that's when you learn the most. You want to prevent them, but if they happen, you learn from them. And in some cases, unfortunately, you lose people in the process, and we don't want to do that, right? Um, there are some root causes of material failures, and I'll pass it very soon to Ignacio. Just want to give some top level view perspective and then go deeper with Ignacio and with some questions with him. But there is root causes of material failures, and they can involve misuse, mishandling. You can assemble things incorrectly with incorrect torque, and you can have a number of manufacturing issues, a number of them: heat treatment issues, surface finish issues, corrosion issues. You could also have the incorrect geometry. You can have the improper maintenance, where an aircraft could experience a crack and it's not looked for, and maybe that'll be an issue. So Ignacio, do you have that experience in your area where you could have some material failures during the life of the program?
Absolutely.
So in your area, like, what would be a component that could be a problem that will require maintenance?
Well, you know, in the energy management industry, one thing that does require maintenance are all the electromechanical connections, right? An electromechanical connection that is not properly achieved can, for example, produce a hotspot. So that would be elevating the temperature of the equipment or the system beyond the acceptable threshold. It can produce, for example, an arc event, which is extremely dangerous, right? Just the massive release of energy as a result of an electrical connection into the environment. And if someone happens to be working on the equipment or just standing by, it can bring catastrophic consequences. So very, very important to keep an eye. And this is the type of situations that you record in different formats, in different documents that can range from all your internal documentation associated to the design, but also to the operation of the product or the system in terms of an instruction bulletin, a user's manual, all the things associated to the proper operation and maintenance of the equipment.
Excellent. So I also want to point out that electromechanical connections in spacecraft and launch vehicles can occur. Those issues can occur, maybe in a different way, but they can occur. So there are similarities here. You can also have unforeseen operations in the conditions. So the aircraft may see, or this launch vehicle can see loads greater than what you had hoped for during the test program. So that can be a problem. You didn't expect those loads to be higher than expected. Quality control could be an issue, like storing, shipping, tracking. Maybe you have composites, and maybe there is an issue with the composites because of the humidity conditions or the heat, or you know, the heat environments can damage the composites. Inadequate environmental controls like improper paint, coatings, corrosion prevention. So you could have inadequate quality control and environmental control issues. And so now what I want to do is pass it over to Ignacio so he can walk us through some of the charts that he's provided.
Yep. Thank you, Professor Goyal. So one of the questions that you had there for me is why is testing so important early in the design phase? To me, testing, simulation, calculation is really important throughout the entire design cycle of the product, of the solution, of whatever we are in the process of developing. And this takes place at different levels of complexity, at different levels of maturity. What I'm showing there under point number one of my recommendations for this is always follow the design process. And typically, guys, when you become engineers in the industry, whatever industry or whatever industry you go, you will find out that there is a design process in place. And the most typical design process that industries have across the world is based on a stage gate approach. What this stage gate approach ensures is that every time you make a significant step or you achieve a significant milestone on your design, there are some requirements that you need to comply with. So in this case, I'm showing our stage gate approach. In Schneider Electric, you can see there that we have an open stage gate. We have the select, we have do, implement, produce, sell, and close. As the design process ramps up, the amount of engineering work becomes more and more up until a point that it gets transferred more to the industrialization function that will take that design and make it a reality. But basically, from the engineering perspective, between the open, select, do, and just before they implement stage gates, it is very, very important that every single part, every single component, every single subsystem, and eventually the system gets checks and balances from all the different cross functions, starting again from the feasibility of the concept. Is it even feasible under the mission profile that it has to serve up, all the way to the feasibility of being manufactured, of being produced, and of meeting different requirements that can come from the customer, that can come internally, that can be the result of a certification agency, for example. But the lesson here is never compromise on really having all the checks and balances on this approach. Missing one deliverable, missing one step of the process can bring pretty harsh consequences down the road. Any questions here? Any comments?
No.
No. If not, you know, the second part of that question is it important to test the product as in service? Absolutely. And, you know, I was speaking about the mission profile. The mission profile captures all the journey that the product or the system will have to go through. Since you know you roll it out of the manufacturing facility all the way until it gets discarded, right? Once it has reached its end of life. But what are the different things it has to go through in terms of operation, in terms of usability, in terms of environmental aspects, in terms of different conditions that will be or that will revolve around your product and system. In many times, the certification agencies will set some sort of a threshold, right? That's the minimum requirement, as I would see, in terms of how your product or system has to react to pre-established conditions. But it's always recommendable to go beyond, okay, to exceed really the parameters that are placed by the certification agency. This will not only give you a sense of security and confidence on what you are putting out there in the market, but it will give you a sense of high quality as perceived from your customers and users. And it will also help you differentiate yourself with respect to the competitor, and most importantly, have a very strong argument should liability come at any given moment of time. So very, very important to take that into consideration. The second point that I have there is really associated to what we call, you know, validation and verification. Okay, and validation and verification is a deliverable that you put together as part of the design life cycle. It is really what will dictate your test plan for certification purposes, and also to be able to meet the mission profile of your product or system. It will also help you check how well you are addressing the customer requirements. So if you see, you know, it looks like a U. It should have looked more like a V for validation and verification. But if you see from the very beginning, everything starts with a recollection of the requirements. What are the requirements? Okay, what is the ask from our customer? Are we getting the request to design, you know, a product with X and Y characteristics? Are we getting a request from the US Air Force. For example, instead of designing a long-range bomber capable of having, X number of miles in range, having Y capacity of payload, what is the ask, okay, from the customer? Once we have that level of input, we have to transform that into offer requirements. And the offer requirements is nothing but the technical translation of what this ask is. What is really the customer asking, and how does that translate into the different functionality, capability, features that our designer system must have. Then the cross-functional team runs an exercise where they extract all these requirements, and then they start putting some boundaries to them, right? What is acceptable, what is not acceptable, what has to be put under investigation. And as the design process evolves, they will be either completely accepting these requirements or saying, you know what, if we accept this requirement, it will have these implications. Are you willing to carry those implications? Yes or no? If the answer is yes, there will be some level of risk associated to it. There will potentially be an impact to the overall timeline of the design. And, on the other hand, if the answer is a no, well, that requirement gets renounced and the team keeps moving. Once that extraction is completed, that's where the architects come into the picture, and they start really deciding and defining how to put all the pieces of the puzzle together. Professor Goyal was making a very good reference a few minutes ago. In the aerospace industry, how do we make sure that once all these offer requirements have been collected, have been extracted, and are being assigned to the different functions, how do we ensure that the synergies, the proper synergies take place, so that at the end of the day, all these components and subsystems effectively become part of a system, right? So in this case, you would have the chief engineer of the structural frame of the aircraft, right? You will have the propulsion specialist. You will have the aerodynamics and control guy. You will have the electrical and navigation guy. Very, very important to have that synergy, synchronization. And again, the test plan at the end of the day will have to be built up in such a fashion that you test at component level, at subsystem level, and at system level. Once all this has been pretty much validated and consolidated, you have to verify it, right? So this is where you start running all the different tests. You validate it just to make sure that whatever you have created meets as much as possible the initial ask. And finally, the acceptance really dictates when your product or your system will be ready to be delivered. Okay. Now, inside these validation and verification efforts, guys, very, very important to be aware of the different decisions that you need to make throughout the process, and the type of tools that will help you, okay? Everything will start from a very simple calculation on a piece of paper, all the way to, running maybe a finite element model of millions and millions of elements, all the way to arriving to a certification agency to execute the physical test. The other very important thing is that as part of this design process and as part of the validation and verification, you have to create, store, and maintain FMEAs or FEMAs, whatever you want to call them. In my industry, we typically use three different type of FEMAs, okay? We use the application FEMA, the AFMEA. We use the design FEMA, and we use the process FEMA, the P FEMA, okay? Each one of these documents will tell you really what can go wrong with your product or your system. The FMEA captures three very relevant parameters: the severity, the occurrence, and the detection. So every single thing that you consider can go wrong from the user perspective, right, which is the application, will have to be stored in there. And this is where you will commonly find things associated to misuse, right? And the misuse can range from a person that didn't really read the user manual or the instruction, or they are completely giving the product or the system a different application from what it was intended to be. The design FMEA captures all the things that can go wrong as a result of a bad design, right? It can be, for example, material selection. It can be form factor decision. It can be the placement of a component. It can be the tolerances that you specify. All those things have to be recorded in the design FMEA. And finally, the PFEMA. This is where you would record every single thing that can go wrong when you are producing the product or the system, right? So, for example, your material has gone bad, right? Because it was exposed to certain environmental agents that have degraded the structural performance of it, or some other aspects in terms of storing, where temperatures were really high, and that has affected the electronic components that go into a control board, for example. So once you run these FEMAs, again, my recommendation is to look for two main things, okay? Look for those items that represent a high severity, okay? High severity means that you're either jeopardizing property, right? So the loss of assets that Professor Goyal was saying, or even worse, the loss of life. Okay, so that's really what a high severity level is dictating. Now the RPN is the product when you multiply your severity by your occurrence by your detection. Okay, in my industry, an RPN of 160 and above is considered to be a high RPN that does require further investigation. And that's when, tools such as the FTA, the fault tree analysis, comes into the picture. The fault tree analysis gives you a more detailed and more granular sensitivity on how likely that item that you are recording is likely to happen, and all the factors that would need to combine for it to become a reality. The FMEA and the FTA become very, very important tools, not only to prevent eventual failures once you have launched the product or the system into the market, into operation, but also because they will act as legal documents should any liability occurrence happens, right? So let's say a plane crashes, okay? If the plane crashes, the FFA will go back and we'll start, reviewing all the documentation. And one of the very first pieces of documentation that I bet they will review is precisely the FMEAs and the FTAs. Were you able to identify the failure mode that produced this catastrophic situation, yes or no? And if you did indeed found it and you didn't take the proper actions, then you will be in deep trouble, okay? So it's very, very important to be as detailed as possible, as negative as possible, right? In terms of, trying to come up with every single thing that can go wrong. And again, for those items that represent a high severity level and or a high RPN, you must take certain actions just to be able to mitigate the impact of those line items. And finally,
I wanted to add something really quick, Ignacio.
Yeah.
Every time that Ignacio talks about FMEA, that's failure modes, effects, and analysis. So failure modes, effects, and analysis. Yeah, go ahead.
Thank you for making that that good clarification. It's such a common acronym to be used in the industry that I should have explained what those letters mean. So thanks for that. And my final recommendation, guys, I've seen the benefits of really bringing a deep understanding of the underlying physics behind, again, whatever product, whatever system you are developing. I started my professional career doing structural simulation. I was doing a lot of seismic analysis, transportation analysis, integrity analysis of metallic structures, of plastic parts of all sizes. But everything starts really by making simple calculations, right? Understanding what is that part supposed to do, what are the different forces or physics really acting upon it. Once you understand, conceptually speaking, and you have run some, let me say, approximations with hand calculations, you can then jump into building more sophisticated models by means of simulation, right? This is where, the power of finite element analysis comes into the picture. That's when you can mitigate a lot of the risks that you could potentially find down the road. But also, very importantly, as software becomes more and more powerful, as you can actually create multi-physics models with a very high level of detail and therefore with a high level of accuracy. This helps you optimize the life cycle of your design, okay? In the past, it was a lot of trial and error, right? You would design something, you would build a prototype, you would physically test it. If the physical test didn't go the way you wanted it, you had to go all the way back to the paper, redesign, create a prototype, and really cross your fingers and pray a lot for it to happen or to pass the physical test. So it became a very iterative process, very lengthy, very costly, and not very, very efficient. With simulation, we are capable of shortening the design life or the design cycle. We're capable of optimizing the amount of resources and investment we need to pour just to make something happen. But also, very importantly, you can optimize your design, and you can see things that you might not necessarily see in a physical test. So be very aware of that. because it's not only an effective tool during design, it can also help you prevent some of these failures that you can eventually encounter down the road. You know, Dr. Goyal was speaking about the Havilland comet with the lousy design of the square windows, right? You know, just imagine if back then, and Professor Goyal, I think that's what, circa of 1950 maybe, that aircraft.
Yeah, yeah, in that era, yeah, early era.
So yeah, I think, you know, if I'm not mistaken, that's probably 1957. I might be wrong, but for some reason I think about that date. Just imagine if the engineers back then would have had a simulation tool that could have told them, you know what, on those squared windows, you will have stress concentration on the corners, and it is the effect of the pressure differential. They would have noted that. They would have made the design change, made those corners rounded, and, you know, avoided a lot of things. Sometimes, you know, we need to really accept reality, and I think Professor Goyal was also saying this. You have to accept reality, and when we do not understand the underlying physics, unfortunately, that learning, that understanding will come when you have a catastrophic failure. Okay. But one of our primary tasks of as engineers, or as soon to be engineers, is to be as effective as possible to anticipate these failures, mitigate them, such that the learnings occur in a controlled environment, occur in a lab, occur in a simulation software, occur on a piece of paper, rather than in real life, and then having to live with all the consequences. Post-mortem analysis is something that we do in my industry, something that the aerospace industry does all the time. And a post-mortem analysis will kind of walk you through in reverse order of every single thing that we have talked, right? And to me, that reduces to only those scenarios where the system, where the environment was so complex that it extended beyond our ability to simulate it, to test it, and that's the price you have to pay for learning.
Yeah,
I'll pause here.
these are excellent points. Any questions from the team to Ignacio? I want to draw a parallel to what Ignacio is talking about to the aerospace industry in this particular page. And, you know, this is very similar to what we discussed in the first step here. You know, we want to follow a design process. And if you cut corners in the aerospace industry, you're going to eventually maybe even face expensive failures. Or maybe it's too late in the process where redesigns could either add weight or could increase costs because of schedule delays and stuff like that. So it's very important to have that building, that stepping stone approach where you're taking step by step, you're improving your analysis techniques, you're improving your testing techniques. And later on, I'm very glad that Ignacio touched upon validation and verification, because that's one aspect I plan to touch very soon. Validation and verification is extremely important in ensuring that the product, the aerospace or the spacecraft or the launch vehicle, meets the requirements from the system level, and then it can meet the requirements for the mission. And so this is very excellent, and a lot of this draws extremely close parallels to the aerospace side. So let me stop and take some questions from the team to Ignacio here. I'd like to at least get 2 questions in.
Hi, I have a question. I don't know if anyone can hear me.
We can hear you. Go ahead.
Okay, awesome. When it comes to aerospace failures due to negligence or deceit, what kind of investigation techniques are used and how do they differ from what we see here so far as far as best practices?
Yeah, so if it's negligence or deceit, uh, uh, you're talking about more into an investigation that can turn into a criminal probe. But we will discuss a little bit later. Negligence and making errors due to not paying attention. Uh, those are typically captured in in some ways in a failure multi-effects analysis. But somebody being dishonest and deceiving someone sometimes is not captured in this because we're hoping that everybody's really working with high integrity. Ignacio, what's your take on that?
Yeah, you know, one of the very powerful elements that a stage gate design process gives you is that it precisely puts checks and balances, right? If I'm being negligent, because I want to cut corners or because I'm just not qualified, there will be people really checking my work and ensuring that whatever I'm saying, whatever I'm proposing, whatever I'm designing is valid or not. On these stage gates that I'm referring to, you typically have a steering committee, okay? And the steering committee is composed by upper management, is composed by experts, subject matter experts, is composed by, really the architect or the authority in the specific design, in the specific step of the process. So you really mitigate any negligence associated to it. The other very strong tool that helps you really avoid or mitigate at least as much as possible is the FMEAs, right? This documentation that you put together where you really brainstorm and think about every single thing that can go wrong. You assign values to the different parameters. Again, if the agency running some sort of investigation in a post-mortem type of situation goes back and they realize that you had indeed detected that failure mode and you took no action for it, then that's when you are completely held accountable, liability. You get a criminal investigation and bunch of not very nice documents, legal documents coming your way. But again, for that to happen is because you compromise the process at some moment of time, because that negligence extended far beyond a single individual. It was more the fault or the decision of a complete group, of a complete organization, and that's when things can absolutely get really, really nasty.
And to add more, even when you have check and balances, even when you have that, sometimes there'll be slips, and it's really hard to capture those in fatal multi-effects and analysis because if somebody on purpose deceits and causes issues that are not of high integrity, it will be very hard to really capture through any perfect process because it's really hard to fight dishonesty, and that's why it's important that you develop high honesty now. And honesty is one of the key ingredients of a successful business.
Good question.
So why we don't go ahead and continue here with what is a successful engineer. But before I hit that, Ignacio, can you tell me a little bit about Uh, how testing and analysis can save the day early in the design process? And you cover a little bit of that, but if you can, go a little bit deeper.
Yeah. So again, the development is a stepwise approach. The earlier you start validating your design, the better off you will be, not only in terms of confidence, but again, you optimize and you bring a lot of efficiencies to the overall time cycle, to the amount of resources that are invested. And this, in many cases, brings very significant advantages, competitive advantages, feature and capabilities of your product, therefore clear quality differentiating aspects with respect to the to the competition. I talked about a little bit of, referring to calculation, simulation, and testing. To me, they have to happen in that order, right? When you are in the very early stage of the design and you're just sketching a concept, run some calculations, have that level of feeling on whether what you're thinking is feasible, and if it is, what are the implications, what are some of the points of attention, what are the things that you need to refine, what are some other things that you might to do a little bit more research on. Once you have, let me say, a first set of concepts, that's when simulation becomes very powerful, right? Because simulation will help you run a benchmark of your different concepts. It will tell you which one has better performance on physics A, on physics B, on physics C. What are the implications of each concept from the industrialization perspective, from the cost perspective, from all other key parameters that you need to take into consideration. And once you have selected a feasible concept, you can drill down into the relevant aspects of it, run more simulation, make that simulation more detailed, more accurate, more encompassing, and that will save you a lot of time, a lot of headaches. It will prevent a lot of frustrations once you arrive to the physical test, either to get further validation of your design or to get certification to it. In my career, guys, I have many times either faced or seen processes where we don't, or we haven't run simulations. So we arrive to the lab and surprise, the test is unsuccessful. And unfortunately, we have to pay for the lab, we have to pay for the certification agency to witness the test. And if we're unsuccessful, that means that we need to go back, invest more time on really figuring out what went wrong and how we can fix it. But again, reinvest or invest additional dollars on securing the lab, on calling the certification agency. In many other instances, because we had a very solid simulation plan and models, we came in to the lab with a very, very high level of certainty. And in many cases, we were happy because we passed right away. In many other cases, because of the complexity of the physics, we didn't pass. But guess what? Because of simulation, we already had a plan B, a plan C, a plan D, whatever the risk and whatever the confidence level was. And, right there in the lab, we either had a second prototype ready, or we had an alternative for a part or component that we can replace very quickly and go ahead and execute the lab again. So very, very important to follow this evolution of how you validate your design, starting from a very simple equation all the way to achieving a certification or a final pass at the physical testing level.
Excellent. Yeah, thank you, Ignacio. And you know, what does it make a successful engineer?
Well, you know, again, 17 years working with a lot of engineers from different backgrounds, from different areas of expertise on different products, addressing different markets. To me, a successful engineer has to be, first of all, creative, right? You know, an engineer, that's actually what the word engineer derives from, right? Being very creative, be ingenious, be capable of solving problems, be very analytical. It's important for you guys, you know, getting prepared to become professional engineers, to understand the foundations, right? You know, the physics, whatever is your area of interest. If you're aerospace engineers, or you feel passionate about aerodynamics, you feel passionate about vehicle structures, you feel passionate about propulsion systems, but you know, whatever makes you feel passionate about, make sure you understand and continuously exercise all the foundations. That will help you not only to build success, obviously, but to me, you know, a key part of being successful is because you enjoy what you do. Okay, so keep that level of engagement, keep that level of interest, feel passionate about it, own it, embrace it, and you know, if you have strong foundations, you know, the path forward will only be very, very positive and incremental. Secondly, you have to be a team player. Okay, being bright, being an expert, but working in a silo will leave you nothing. Okay, whereas, you know, operating in diverse environments, being very open, you know, to share knowledge, to share ideas with others, but likewise to keep your ears and eyes open to someone else's ideas, to someone else's proposals, will certainly make you very successful. Step up to new challenges. You know, throughout our careers, sometimes we're not prepared for that next big thing, but just trust yourself, trust your past, your preparation, your foundations, and be the one, you know, taking that step forward, saying, I will work on this, I will develop that, I will research, I will find a solution, but this is the team that I would like to work with and support me. So again, very, very important to operate as a team player. Thirdly, and you know, Professor Goyal was also mentioning this a few minutes ago, integrity. You know, when you're an engineer, your actions will have consequences, right? And the consequences can go from, you know, just delivering a lousy product out there in the marketplace with poor quality, maybe having to make a massive recall of that product, all the way to producing loss of human life. So always act with the highest level of integrity. Always be very aware about the implications that your actions will have. Use the knowledge that you have on the underlying physics just to understand, you know, what can go wrong, or how do I improve this? What can I make better? and understand also the business impact of these decisions, right? As engineers, sometimes we can create, the best machine, the best product, the best system out there in the world. But if there's no market for it, or if it doesn't quite meet the mission profile or the ask of our customer or a target cost, then the chances of that product, of that development, of being successful significantly decrease. And finally, always be very, very positive. Look for constant innovation, but never, never forget about history, okay? It's always very important to be aware of all the lessons learned that have happened in the recent past, 10 years ago, 20 years ago, 50 years ago. I mean, the aerospace industry in particular, it's a very innovative industry, right? Particularly nowadays. But we cannot only look forward. We have to be very self-conscious about all the different things that have happened in the past, all the different learnings that have been collected. All those events that have dictated, what the aerospace industry is nowadays. So those are my recommendations. Again, any questions, any comments, anything you would like to share, I would greatly value that.
I actually have a question. I mean, because you gotta have like all these things that are important and great and whatnot. Could you give an example from your personal history, one that was just kind of like really impactful in your work experience?
And I'm sorry, I missed a part of it. Just say that again, please.
Oh, no worries. I was just wondering, could you give us an example of some experience that you've had working within your industry that was just, I guess, really interesting or really impactful? Yeah. Just some situation. Be cool to hear.
Yeah. So I'll share with you guys the project that I'm currently working on, and I'm extremely excited and proud at the same time of what we are still in the process of accomplishing, because this is a system that we will launch actually in California, Q1 next year, probably on the February-March time frame. But what this system does is really creates a residential solution for what we call the new energy landscape. It helps us achieve a very optimized and effective convergence of different energy sources that you can find in a modern house. Not only the energy coming from the utility, but also the energy that you are able to generate from a solar photovoltaic system, from a battery, from a generator, with a lot of intelligence built into it, different control functionality. But for these guys, everything started with a sketch. Somewhere probably call it September, October of 2018. We were just discussing on a table in a meeting room what could be the next big thing for our industry, and we literally started sketching some ideas on the whiteboard in that meeting room. We thought it was a good idea. We thought, the market, the dynamics, and most importantly, the ask from, different stakeholders was there, and that could make this system very successful. So we embarked on the stage gate design approach that I showed on the previous screen. we put together a business case. We said, okay, this is our projection in terms of number of units. This is the price at which we believe we will be able to position the solution. This is the target cost, okay, because we want to achieve some level of profitability. And we started putting together the offer requirements. The offer requirements, for you guys just to have an idea, that is a Word document of about 10 pages, okay? And those 10 pages contain just statements, right? Saying, okay, you know, the system shall feature this functionality. The system shall be of this color. The system shall meet this specification. So 10 pages of really requirements that our engineers took, they transformed into technical requirements. And because it's a very complex system from the energy management perspective, there are a lot of functions involved inside Schneider Electric, but also outside Schneider Electric. There are other companies working for us, inverter manufacturers, battery manufacturers, generator manufacturers, energy monitoring manufacturers, you know, control functionality. So it's really a system that has a lot of components coming from different parts, and at the end of the day, everything has to work accordingly to the mission profile. There's nothing out there currently in the market, so it's targeted to be a very significant innovation in terms of how we conceive the electrical distribution and the energy management in a house. And we have done, you know, a lot of simulation, short circuit simulation, which is a multi-physics type of situation where you have a combination of structural effects with energy thermal effects. It's a dynamic type of event, so that adds complexity to the model. It's a thermal type of simulation as well, just to check how far or how close we are to the limits, in this case posed by underwriters laboratories, which is the certification agency, and that has given us confidence. We were very successful actually passing the physical tests at the first trial. So a success story of the importance of calculation and simulation. And you know, just to maybe finalize my story here, we have been working on this project for about 12 months. Okay, and today we were reviewing the first physical prototype of it that will go for approval, you know, with different regulation bodies in California. But that's really the first time this prototype will go outside our boundaries, just to get the external validation from other stakeholders.
That was a great question and a great response to that question.
Yeah, thank you so much.
And guys, I had a lot of fun populating my application FMEA. Believe me, it was quite a journey. You know, at the end of the day, I think I had maybe 4 or 5 severity 10 events. I believe I only had 1 RPN exceeding 160. But you know, that's when the importance of operating in a team comes into place. And you know, we have the quality function, the industrialization function, the design engineering function, saying, okay, that's something that could happen. The severity is absolutely putting actually you know, human life in danger. these are the actions that we need to take to mitigate, the occurrence of that event, and also the severity should it happen. So very very powerful exercise, because when you're running such a thing, you start thinking about many things that you might have not necessarily thought about earlier in the process, but it gives you the ability to still go back and make the proper adjustments, the proper modifications to ensure a very, very solid design.
That's an excellent response. Thank you so much, Ignacio. Any other
No, great,
questions?
great question. Thank you, guys.
And so what we want to make sure is that as you go and progress through your career, you understand that it takes more than just numbers, right? We want to be able to work with a team and ensure that we are maintaining high level integrity, that we have passion, that we're great communicators, and that we know how to overcome challenges as a team instead of blaming each other, right? So some of the ingredients that Ignacio has talked about. I'm going to step through some examples of failures that have occurred due to issues that we have seen in the past. The Boeing 757 had a tearing in 2010 in this area here, and that was near the left passenger door, and it coincided with an area of the fuselage that did not meet the thickness specifications in the chemical milling process. And as a consequence, a crack started to initiate due to fatigue in the fuselage crown skin. And so Boeing issued a basically a service bulletin. And anytime there's an issue in that industry with an aircraft, a service bulletin could be issued by Boeing or their manufacturer to alert everybody to look for implementing certain inspections or maybe even making modifications to the design. In this case, they're asking for performing external inspections about every 300 flights hours and to look for cracks in the area because of that issue. And so you can see how the chemical milling process caused that issue. There was a bad repair, as an example, of Japan Airlines Flight 123. There was a catastrophe, and the poor repair was performed due to a tail strike, which used a doubler plate on the rear bulkhead. However, the repair was not properly carried out per Boeing repair methods. The proper method called for one continuous doubler plate, but the technicians used two plates instead. And so the use of these plates lowered the fatigue life, and so that will then led to failure event. And the point here is that I want to make with these two examples is that a failure modes effects and analysis was done early in the program. And then after this failure occurred, a failure investigation had to ensue. So having that failure modes effects and analysis was extremely important for them to pinpoint the issue of concern. And you can see here that these are errors occurring during the production phase when you didn't think that there would be a problem, there was a problem. And so we call that a lot unknown unknowns. You just don't know. You plan for everything, and that's a plan. You want to plan for everything, every possibility. But there are certain things you may not be able to control because we're all humans, right? The China Airlines flight also had a failure caused by a repair as well, and the faulty repair was also after tail strike. So very interestingly, and it was not conducted according to the Boeing manual, and the damaged skin was removed, and the doubler plate was overextended, and that was done to basically restore the strength. And the investigation showed that the damaged skin was not removed, and the doubler plate only covered the damaged area, not overextended. And so fatigue life again caused the failure. And examples of other space failures is the Titan 34D. It exploded during ascent. We have the composite rocket failure, Delta II, which exploded as well during ascent. And then we have the Space Shuttle Columbia breakup, which we'll talk a little bit later in this lecture. We have 3 space system Loral satellites experience composite failures due to inadequate venting. And what I mean with that is that as the spacecraft ascends, the outside environment drops to zero, the pressure. But the inside of the honeycomb sandwich core, which is manufactured on the ground, will maintain pressure. And so that differential pressure when you go to space across the phase sheet, basically with potential weakness in the bond line, cause a failure. And what you see here is something interesting. 2004, 2011, 2012. So obviously this failure occurred 3 times. Obviously, you can see here that maybe the lesson learned was not learned, or we didn't know what was going on the first time or the second time. But the important thing to remember in your career is do not forget the lesson learned. That's a lesson learned. Do not forget the lesson learned. That could be one lesson. Another lesson is that when a failure occurs, to make sure that you mitigate all potential causes. You don't want to zero in into one potential failure scenario and just focus on that and do nothing more. And the reason you want to be careful is because if you just focus on one failure mode and you didn't look at the other ones and you thought you got it right and you got it wrong, then those other failure modes that could have occurred could come and creep in and cause a failure again. There's also a hypersonic test vehicle that experienced an anomaly during reentry, and it was attributed to the aerosol composite degradation. And you can see more of that, in the open literature. Here, I invite you to pause the video at some point, and I want you to download this paper, which goes into the investigation of space launch vehicle catastrophic failures and walks you through a number of space launch vehicle failures since 1984 all the way to 1994. And you will see there how the cause and failure of the failures was found, what corrective action was taken after the failure occurred, and the issues that are weak in each vehicle. And you will see that there can be a number of contributors from structures, propulsion, and a number of other disciplines. Here's an example of the radiator phase sheet failure. The International Space Station heat rejection system radiator phase sheet failure occurred. And again, it was an unvented situation where the air could not escape when we went to space, as an example. So failure investigations, involve really having that foundation, that failure modes, effects, and analysis, and then moving on through the fault tree and the fishbone. You can either use a fault tree or fishbone. There's 2 approaches to that. Failure modes, effects, and analysis. What is the benefits? And Ignacio went through a lot of that. It allows us to identify areas of the process that will have the most impact to the customer. It can help us identify how our process is most likely to fail, and it will point to process failures that are most difficult to detect. Application examples include manufacturing, design, and software. So for example, manufacturing. A manager is responsible for moving a manufacturing operation to a new facility. So we want to make sure that when you make that move, everything goes well. You don't want any surprises. So you could then perform a failure modes, effects, and analysis. If you have a design, again, a failure modes, effects, and analysis, you want to know every way a product can fail, because you want to make sure that product is robust to those failure modes. A software is another example of where failure modes, effects, and analysis can be applied. The FMEA is a methodology, and it helps to facilitate implementing process improvements. And it can be developed based on brainstorm exercises. You can have engineers in one room trying to understand, and you want brainstorming from many team members, many different disciplines, to make sure you're not missing something. Ignacio, you want to add something to that from your experience?
Yeah, I mean, absolutely. The FMEA is a cross-functional effort, right? There's a function, or there's an individual taking the lead, Again, from the application perspective, that in my case is software management. So that would be my team and I. The design, it's typically the project leader. The process, FEMA, it's typically the industrialization process leader or the industrialization quality leader. But in every single one of those three FMEAs, you have cross-functional participation, quality function, purchasing function, the product architects, engineering, offer marketing, business development. So, you can really invite as many people as you want, and the more functions you have, the more encompassing and the more robust of a document you will have. The other important thing to keep in mind is that the FEMAs are living documents, okay? You need to give maintenance to them. You need to constantly update them. You need to make sure that they always match the latest version, the latest generation of whatever your system or product is.
Excellent. And I think in general, FMEAs helps you eliminate issues with it. Issues that could occur early in the design process as well. And also FMEAs can estimate the risk, like Ignacio talked about. It can also help you prioritize what action should be taken to reduce the risk, and it will help you to evaluate the design and the validation, and also the processes. So when to conduct an FMEA? Early in the design process, and you also want to do when you're early in the design process, but when you're implementing a new system, you also can implement it in existing design. So I've seen situations where a FMEA did not exist and it was developed later in the process. Unfortunately, that could lead you to some redesigns, or it could lead you to some mitigations to pay attention to that those things do not happen that could go wrong. You could also apply FMEA when you're carrying on over a design to new applications. And again, you could also do it for different processes. So when was the FMEA really first used? It was used first in the 1960s in the aerospace industry during the Apollo missions. In 1974, the Navy developed the MIL Standard 1629 regarding the use of FMEAs. In the 70s, the automotive industry then adopted it, and they were really driven by liability costs, and so they implemented FMEA. Later, the automotive industry saw the advantages of using this tool to reduce risk related to poor quality. Here's an example of what a FMEA table could look like. I'm not going to say that this is the way it looks like for everybody. Every company is going to have a different type of table. But the important aspect is that you're going to have you're going to identify the failure modes in these columns, and you want to make sure basically what ways you could go wrong. Basically, that's what goes here. Identify the causes of the failure modes and controls in these two columns, and then you will go into the prioritization to basically look at the occurrence, like what severity, occurrence, and detection, the RPN number that Ignacio talked about, and then determine and assess actions. That goes here. So that's kind of a top level view. Ignacio, anything on this?
Yeah, no, I think this very well illustrates the different parameters that we were referring to, right? Severity, occurrence, detection, the RPN, which is the product of the three of them, and then again, at least in my experience, the practice that I have on FMEAs, whenever you have a high severity and or a high RPN, your own industry will dictate what the threshold is. It's very, very important to always associate a recommendation and fill out what are the actions taken. And as a result of that, you will repopulate your parameters to see how effective that action really is.
There you go. I totally agree. And types of FMEA, we talked about design process FMEAs. a team approach is completely necessary. And you need to have members of every department you can think of to make sure we have a complete FMEA. And one other thing I want to point out here, and this is more of a learning experience, just like you guys have personalities, your team is going to have personalities. And that's something I want to bring to your attention. You know, you're going to have, when you're forming that team, you're going to have some challenges. Everybody, you know, not everybody knows each other. Everybody wants to have an ego. Everybody wants to get promoted. Everybody wants to be heard. Some people may not want to be heard. They're very quiet. Some personalities will feel intimidated. Other personalities will be overtaking. So you're going to have that stage where you're forming a team that's diverse, that's going to be critical for the development of these activities. But then you're going to have a second stage called storming. And that's the second stage where the team starts to work together and they need to gain each other's trust. Initially, that process is tough. You're going to have people raising their voices or not listening to each other, or conflicts could arise because of ego coming against each other. But then there will be a time where the team starts working very well together. And if you're a lead in a FMEA and you're developing this process with the team, just keep in mind to be patient. Try to walk the team through this process in a healthy way. Don't start to create chaos right after storming or during storming, because after storm, there's always calm. And so it is important to then go into norming, where you start to resolve disagreements. And that happens during happy hour sometimes even. You'll be surprised, or bringing a donut, or having a spirited conversation about sports. You know, maybe your football team or the basketball team. Um, but this needs to happen. This process needs to happen. And then there'll be a time where the team will start walking towards a common goal and they'll perform really well. But it's up to you as a lead or part of the team member. Even if you're a team member, please recognize that this could happen. Ignacio, any thoughts on this when it comes to FMEAs and team environments?
No, I think you hit it right on the nail, right? As this exercise evolve and as you have the presence of different functions, you will obviously have different personalities. Just keep an open mind. There are really no bad ideas, no bad pieces of input. Everything has to be considered. Everything has to be evaluated, and then as a result of the consensus of the team, that item will formally get documented as part of the AFMEA or further refined until they arrive to a point that they consider it valuable to store it in there. But you know, it's natural, and I think all of us have faced that situation where you have to um, work or interact with different types of characters. Just understand that this is a process that everyone has their very own way of expressing their opinion. So just participate actively, and if you are managing the process, make sure that everyone gets heard and that all the inputs are considered relevant and important.
Great. Any questions from anybody to us? Okay, great. So let me continue here. The familiar procedure for each process input. You know, you start with high value inputs and determine ways in which the input can go wrong. For each failure mode, you want to figure out the effects, you know, and select a severity level, identify potential causes of each failure mode, and then you want to select the occurrence level for each cause. Then you want to then list the current controls for each cause and select the detection level for each cause, and then develop recommended actions, assign responsible persons, and then take those actions. So that's kind of like the top level view. You're going to be doing some of that. And, you know, severity is importance to the customer. In aerospace applications, you know, if it's mission critical, then it is highly important regardless. The occurrence is, the frequency in which that given cause can occur and create failure modes. And you usually rely on past data. Sometimes it's based on engineering judgment. And then you have detection, the ability of the current control scheme to detect and prevent those issues. Ignacio, from your experience, how do you really formulate the occurrence? Because that's a tough one. If you don't have the test data or any data, occurrence can be very tough to figure out. And in the aerospace industry, we often use engineering judgment and experience from the gray beards of the company, we call them.
Yeah, in my industry, really occurrence criteria is based on the collection of data coming from the past. We start, for example, for us, a ranking of 1 in occurrence. It has to do more with a very, very remote possibility of happening. And the way we define that is if there are any similar parts that have been used in previous design and that failures have not really been reported or identified, right? Whereas, for example, a level 10 occurrence is that the failure is pretty much a given, right? Is virtually guaranteed. That it's something that has been very present in the industry, that it is known to happen. And with that, we build the different shades of occurrence, right? But there is certainly some historical data supporting this.
Really good. Thank you, Ignacio. And then you have the rating scales that Ignacio talked about. I invite you to pause the video later and kind of look at this carefully. And then here you have your levels, rating scales for severity, occurrence, and detection. Not easy to detect 10, very likely 10, very severe 10. Failure investigations in the aerospace industry. There is a very nice guide called the Root Cause Investigation Best Practices, and it's the TOR 2014-02202. I invite you to pause the video and download this particular document. I think you will enjoy reading through it. And when you conduct, and now I'm basically stepping to failure investigations. Basically, what I want to say here is failure modes in effects and analysis can really help you when you step into a failure investigation. And so, failure investigations, you want to make sure you have not an incorrect teaming composition. These are the things not to do: incorrect data classification, lack of objectivity, cost and scale constraints, rushing to judgment right away, lack of management commitment, lack of insight. These are things we want to avoid in a failure investigation. In a failure investigation, there are steps we care about. We care about containment, preserving the scene, especially if it's an aircraft investigation or spacecraft or launch. You don't want to contaminate the scene. Communication and documentation are extremely important. Creating a team that's complete, and then performing a failure review board and starting a process that's formal to walk you through the evidence. You also want to collect and classify data. You want to define the problem and perform a root cause analysis. For each item that we're concerned about, we want to really perform a root cause analysis. And then for issues that have been identified, we want to implement a corrective action plan, and then implement that and verify and then validate it to make sure they're effective. And then you want to return back to step 6 if the problem continues. But here in this process, you may want to do some analysis and testing to kind of validate those issues. So the key questions you want to ask in a failure investigation is: who should be involved? Who should be present? What was their role and location? Who was involved in that failure? What organizations were present? To what extent were they involved? Are there any witnesses? All parties present, and if there are present, should be considered as witness, not just anyone there. Who was in the previous shift? And I'm talking about here, this could be people in the manufacturing floor, as an example, that maybe an adhesive was used and it was a wrong adhesive, or the solder joint was created with a wrong material. So these are people that could serve as witnesses. And so you want to basically walk through all the steps from beginning to end. What happened? So that's the question. What is the sequence of events? What hardware and software and processes were in use? What operation should be performed? And, you know, did it occur during normal or special conditions? As an example, an airplane that's flying through a thunderstorm and crashes, perhaps hail damage caused a problem. There's an Air France 447 that crashed when it left Brazil, and it crashed in the Atlantic Ocean. Well, it went through a thunderstorm. Now, it was not necessarily a structural failure, but it was other issues playing a role with the pitot tubes, as an example. So, yeah, those conditions were not normal, and that can help you start pinpointing the areas to focus on. What were the settings or modes or on all relevant hardware and software? So, basically, you want to make sure that those settings or modes were the correct ones for the application. Also, it's important to really gather a clear timeline. And in the spacecraft and launch vehicle industry, this is huge. If you have a failure that occurred at T plus 1 minute with 20 seconds, you can look at the telemetry and see if there's anything weird going on prior to the failure. In fact, many anomaly investigations in the aircraft, launch vehicle, and spacecraft are solved using timelines, or not solved using timelines, but timelines provide significant guidance because it gives you telemetry, it gives you acceleration data, thermal data, strain gauges, accelerometers. You can have a lot of data, pressure sensors. And so maybe the pressure sensor was acting weird in one of the valves. And then the failure occurred. Well, maybe something was going on with that valve. And that's why it's important to pay attention to the timeline of events and creating a timeline that sync with the video as well. What's the location of the event, and the environment, the pressure, the temperature, what was going on nearby? Lightning? Was there lightning? Hail? Hardware configuration for the spacecraft and the working space dimensions, working conditions, because the working conditions could also have been a problem during the manufacturing of the parts. And so what documentation we're looking at? We're looking at a lot of stuff in a field investigation. We're looking at drawings, checkout logs, test and checkout record charts, launch records, weather information, telemetry, video, audio, time cards even. You'll be surprised. Training records. We found situations where a manufacturer or quality person that's working on the floor, technician, was not trained properly. Work authorization, maintenance inspections, problem reports, notes, email messages. You'll be surprised. There could be emails going back and forth internally within the company saying, we're concerned about this issue. And nobody's taking action in the management chain. And we'll talk about that in the context of the Challenger and the Columbia investigation. But automated log keeping systems, visitor logs to see who visited the facility, procedures, collection of observed measurements. You don't want to miss any critical data, because the minute you zero in into a particular failure mode and root cause, you want to make sure you didn't get blind. You're just blinded to just the one thing and not paying attention to the remaining things that could have played a role. Another key question is, knowledge of group dynamics, understanding how teams work together, the ability to read the team regarding confusion. You're going to have a lot of people that have pet theories during a failure investigation. They have their own theories. But is that theory even reasonable? That's something that you want to discuss as a team. You want to create a safe environment. You want to deal with intimidators like we discussed earlier. And the ability to determine if the team is diverse enough, and making sure that the team is complete. Also, in a failure investigation, we have seen teams sequestered for weeks to make sure that no data is getting disclosed outside of the failure investigation team. That in a failure investigation, you're going to see teams working many hours to completely close the investigation, but also to make sure we don't have data pollution. You also want to make sure that, what can the team do differently in order to cause this kind of problem. You also want to approach the problem from the creative perspective, and also from the logical perspective, both sides, creative and logical. You also want to classify data to clearly identify those items which are factual. Ignacio, anything you want to add on that? And I'm going relatively fast.
No, I think I'm good.
Any questions from the team? We do use root cause analysis tools in which the team will feel the most comfortable. So not everybody is used to a fall tree. Some people are more used to a fishbone. There's two approaches. There's several ways. You just want to be very flexible and work with the team and drill down as many. You want to drill down as deep as you can and as wide as you can until there's no further actionable causes. You want to identify root causes, contributing factors, undesirable conditions. Then you want to prioritize them and determine which will occur first. So it is very critical that all branches of a root cause analysis be exonerated or eliminated. And if you cannot eliminate it, then you probably want to start working at mitigation and really applying corrective action. And there are times where management, and I would like to hear from Ignacio on this, sometimes management, is pushing the team really hard. Hey, what is going on here? We have a product that needs to go out. And so there is a balance. You guys as engineers, you'll be faced with a balance. Do you want to sacrifice your integrity and tell people, no, I got it done, that and gone really fast, look at this? Or you're going to be honest and say, no, I need more time. How you draw that balance is very tough as an engineer, because you don't want to get fired for not doing your job, but you also want to get praised. A lot of people want to get praised. Not everybody wants to, but some people want to get praised because they want to get promoted. And so they want to turn whatever. I turn whatever and we're done. No, I mean, there needs to be a balance. And you're going to see that push and pull from leadership and engineers at the lower levels. You're going to see always that tension where the engineers say, oh man, they're pushing me so hard to get this done. And leadership is, really trying to push that in the other side, saying, okay, they're taking too long, they're becoming too engineering-like, they're not looking at the big picture perspective. Ignacio, you want to add something to that? Because that happens all the time.
Yeah, I mean it's a common challenge that we all face, right? That is why it is extremely important to have a proper planning, really anticipate with enough amount of time when the deliverables need to be turned in, at what level of maturity, how long will it take, to collect the different feedback, how long will it take to make sure you have all the cross functions present into the meeting. And if you really find yourself in a situation where they're putting pressure, never compromise, right? It goes back to the first suggestion that I made, point number one. If you have a stage gate approach and you're doing good planning, that will help you, eliminate, if not eliminate, certainly mitigate these type of challenges. You can still face them, but never compromise again because of all the implications that it can derive as a result of this.
Very nice. Thank you so much. You also want to use, good sense. Good sense. Making sure that we are following the process. You also want to use the NOT system. Basically, what you need to know, what needs to be known for sure, need to know for sure. These are opinions. Maybe, maybe we need it, maybe not. And we think we know. And so these are very useful because it will let you decide and prioritize what's important to pursue. For example, I would really need to know the humidity and temperature versus here, the belt speed on the machine appear to be slower than usual. That's an opinion. So you want to basically find witnesses to help you figure out what's going on there. But you may not have all the data. In every failure investigation, you may not have all the data. The operator said he or she was having difficulty cleaning the contacts. Well, that's an opinion. So look at the interview, or maybe have them recreate this event to see if they can have that difficulty. Press head speed was at 4,500 RPM. Well, we think we need to know, but you can verify that by review of press head logs. So some information is already recorded and you don't have to do much. Oily substance on the floor, we need to know that. So, okay, how do I find out? Interview cleaning crew. So that's an example. So the knot is very helpful. And so again, questions that you want to ask: what happened? Where did it happen? Who observed the problem? How often did it occur? And is the problem repeatable? So now what we want to do is conclude this particular lecture and basically hand it over to Ignacio for any final questions to the class or any concerns that you may have. Let's go through that now.
I know I do have a question for the class.
Yeah, Ignacio, go. So hold on. So Ignacio, go ahead and ask your question for the class.
Do me a favor, Professor Goyal. Go to the slide where you were describing the problem with the Boeing.
So we have this one.
That one right there. I think this is a very good example, guys. And if you were the engineers, in charge of designing this aircraft, what do you think it would have been proper or appropriate just to prevent this type of issue? Where do you think you might have discovered and anticipated this type of issue?
Could it have been discovered within the quality control department?
Good. Yes, certainly. Quality control. Once the section has been produced, someone comes in and checks the dimensional compliance of the part or the assembly. Very good. But maybe even before that, before the part or the assembly gets manufactured.
In finite element analysis.
Finite element analysis could have helped us for sure, just to simulate, okay, what happens if there's a crack here, what would be the rate of propagation, what would be the end effect. That's a good point. But maybe let me say, before running a simulation, how you could have known that a simulation can deliver important answers to you? So there are two important things in this case, right? One is that the area of the fuselage did not meet the thickness specification. That's number one. And the second one is there is a chemical milling process associated to the creation of this area of the fuselage. So how do you think we could have anticipated this issue, really?
Could it have been within the chemical milling process in terms of, I'm not really sure how to word it.
I'll give you a 4-letter hint. Can you guys guess what that 4-letter hint might be?
FMEA.
Exactly, right? If I'm the engineer, I could have stated in the design FMEA, if we are unable to meet the dimensional specification or the tolerances in this part, this could happen, okay? And because this could happen with this level of severity or with these RPM levels, okay, this is the action that I will take. And maybe the action was for me to be very clear on the drawing to say, you know, what the tolerance should be for the finished part. Okay, very important to take that into consideration. For the finished part, it has to be within these tolerances, because if it's not, this can happen. And because I don't want that to happen, I'm gonna take this action, right? The second thing could have been for the person in charge of industrialization to say, well, you know, if the chemical milling process is not adequate, I can damage the dimensional integrity of the part, and that's going to produce this type of failure. Therefore, these are the controls that I need to put in place in my chemical milling process to make sure that I don't degrade the dimensional parameters of the assembly. This is an excellent example, guys, on, you know, things that should have been recorded on the FMEA and they weren't, or if they were, there were no concise actions or effective actions that could have prevented this from happening. But good comments and good ideas.